In this video, I'm going to talk about the ratio data type in Zen. So the ratio data type is a way to store a frequency ratio such as 5 to 4. And so to create one of these, we simply put a colon between two numbers, and it constructs a ratio for us. There's another way to create this type of data, and it's to use this ratio function, which works very similarly. You just pass two numbers. You can also just pass 1, and then it'll interpret the second one to be just 1. So another thing we can do with these data types is, let's say we have, so this is actually an ET data type, which is an equal tempered value. A command that's actually built into the console as opposed to the language is if I just type this colon operator and nothing else, then it converts the last value to a very close ratio. And so I can actually look at how many cents that is with a similar sort of command, and it looks like it's almost exactly 400 cents. And it just ends up being a very complex ratio because there's not really a ratio that can represent the square root of 2. Another thing to mention is the built-in constants for the language. So this 504 is a just major third, and it's so common that there's actually a constant called third that stores this value. There's a constant called fifth that stores a just fifth, and there's a constant called seventh which stores a just seventh, like a flat seventh, if you use the seventh harmonic. There's also octave, which stores a 2-to-1 ratio. So with these values, we can combine them in certain ways in pitch space, as I mentioned in the last video. That's where all the math happens. How about we calculate a certain type of comma, I guess, a diesis, which is the difference between an octave and 3 major thirds. And so I'm actually going to define it as a variable. That's not how you spell it, diesis. It is an octave minus 3 major thirds. So I'm defining this variable and I'm equating it to this value over here, this value of this expression. And I'm just going to replace these guys with their constant values, because these are actually stored as the same thing as I showed you. And so now that I've computed that diesis, I can just use it wherever. It's 128 to 125 as a ratio. And there's also another comma we can figure out mathematically, which is the syntonic comma. Syntonic comma, so this is going to be another variable I'm defining. And that's the difference between, let's see, I think it's 3 to 2 ratios. So 4 fifths minus a major third. So I do 4 times fifth minus third. And so, well, you notice when I get this value, it's actually pretty big. It's larger than an octave, because I'm subtracting the small value, a third, from a pretty large value, which is 4 stacked fifths. And so, of course, the actual syntonic comma is the same sort of interval, but put within 1 octave. And so I have a function normalize, which will do that for me. And actually, I can do it like this without capitalizing this C in syntonic comma, because the entire language is case insensitive. And so now we have the actual syntonic comma, and I can redefine it to be that value. And actually, another way to do this operation of like taking something like this and putting it within an octave is to actually say, here, this variable answer actually stores the last return answer, by the way, is take the answer and take it modulo an octave. And so what modulo does in terms of pitch space is you can think of it as we're trying to divide this big interval by an octave, and it's, you know, it's some certain large interval, and really that large interval is a smaller interval plus a bunch of octaves. So modulo actually finds the remainder when we divide this answer, which is this large interval, by an octave. In the case of the octave, it happens to be the same as putting something within the span of an octave. So another capability built into the language is creating compound ratios. It's very common to see people talk about sonorities as a sequence of partials in the harmonic series. So for example, this is the 4th partial, the 5th partial, the 6th partial, and the 7th partial. The colon operator is overloaded to create these kinds of things as well, in addition to just converting and creating stuff this way up here. And this actually creates a list, and I'll go over lists a little bit more in a future video, but this is essentially the same as taking that portion of the harmonic series. Another thing we can do with ratios is to flip the way they're oriented. So here we have this ascending just major third again, and I can just put a negative sign in front of this ratio, and it'll just flip it. It'll invert it. So now it's a descending major third. And notice that that's different than taking -5 and trying to make a ratio of -5 to 4. You can't do that. We'll get an error because frequencies can't be negative with what we're working with here. So this negative sign actually is applied to this bit after it's constructed. The last thing I want to show is conversion into ratios. So I showed this. We have this ET value. We can easily make it into an estimated ratio. But we can also use this ratio function for similar capabilities. That's about it for ratios. In the next video, I'm going to talk about equal tempered values.